Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present types of fillers in epoxy resins. Fillers are often used for the sole purpose of reducing the raw material cost of the epoxy system. Fillers that are used for this purpose are often referred to as extenders. Extenders may also provide one or several secondary functions in addition to cost reduction. However, their most distinguishing features are their low cost and availability. Extenders can be inorganic or organic. Inorganic extenders are primarily naturally occurring minerals, and these are often used in epoxy formulations. Organic extenders are naturally occurring resins or fibrous particles. Inorganic extenders are minerals that are commonly used in epoxy formulations. Calcium carbonate is the most commonly used extender. Calcium carbonate is available in many different particle sizes and in various grades. To improve dispersion in certain resins, the filler is often coated with calcium stearate or stearic acid. Silica is also often used as an extender in adhesive formulations. Similar to calcium carbonate, silica is an abundant mineral found in crystalline form, quartz, and amorphous or diatomaceous silica. Silica is used more extensively than quartz because it is providing fewer machining and abrasive problems. Although it is an excellent additive for increasing viscosity, diatomaceous silica has a low oil absorption and very large surface area. Therefore, it cannot be easily incorporated into formulating in high concentrations. Kaolin clay is another naturally occurring mineral that is often used as an extender in adhesive formulations. It is hydrated aluminum silicate with the hexagonal plate-like crystal structure. In addition to reducing cost, kaolin clay provides shrinkage control, dimensional stability, viscosity increase, and also pigmentation. Talc is a hydrated magnesium silicate which is used for lowering the cost of the formulation with a minimal effect on physical properties. Because of its plate structure and aspect ratio, these extenders are considered as reinforcements also. Organic extenders. Organic extenders are primarily of two types. Fillers derived from organic materials and low-cost, naturally occurring or synthetic resins. Of the first type, which has relatively high aspect ratio, wood floor, shell floor, and other cellulosic fillers are the most common. Petroleum-based derivatives, soluble lignin, and synthetic resins are of the resinous types. A coal tar pitch is the most widely used resinous extender for epoxy resins. It is primarily used in surface coating formulation in the marine, pipe, tank, and general industrial maintenance areas. High boiling point petroleum-derived bitumes are also used as low-cost extender in epoxy formulation. However, an alkyl phenol must be present as the compatibilizer between the resins and the extender. Further resins can also be used with epoxies to reduce costs and obtain increased resistance to acids. Fibers for bond line thickness control. This is generally relative to the epoxy adhesive formulations, and generally fillers are incorporated to control the viscosity of the adhesive as well as other properties such as thixotropy and sag resistance. If the adhesive flows easily before and during cure, there is a possibility of adhesive starvation at the joint. On the other side, if the adhesive follows only under great external pressure, there is a risk of entrapping air at the interface and too thick of the bond line. These conditions result in localized high stress areas and a reduction of the ultimate joint strength. Flow characteristics can be regulated by the incorporation of fillers or woven tapes referred to as internal shims. To obtain a practical bond line thickness after the application, fillers are incorporated. Ordinarily, the objective is to bond line thickness of 2 to 10 millis at pressure as high as 5 psi at the curing temperature. It should be noticed that the viscosity of the formulation could drastically be reduced at elevated temperatures, and there is a risk of adhesive flow out from the joint area before the adhesive is completely cured. Glass, nylon, polyester, paper, and cotton fabrics or mats are often used as a carrier in tapes or film epoxy adhesive systems. Glass or polymeric microballoons incorporated directly into the adhesive formulation can also be used for this shimming function. The coefficient of thermal expansion of the epoxy resin is a crucial factor in adhesive systems. Often the difference in the coefficient of thermal expansion between the substrate and adhesive will result in internal stresses in the joint. Here the aim is to reduce the internal stresses that act to degrade the joint strength. These stresses are also dependent on the substrate type, the curing temperature, and the service temperatures. When a liquid adhesive solidifies, the theoretical strength of the joint is reduced because of internal stresses and stress concentration that usually develop. These stresses occur when the joint is taken to a temperature that is different from the curing temperature or when it is exposed to thermal cycling. The most common causes of internal stresses is due to the differences in thermal expansion coefficient of the adhesives and the adherents. Using a resilient adhesive that deforms with the substrate during the temperature change is a possible solution to the expansion mismatch problem. However, the creep of the adhesive is possible here, and also highly deformable adhesives usually have low cohesive strength. Another approach is to adjust the expansion coefficient of the adhesives to a value that is closer to that of the substrate. This is generally accomplished by incorporating specific fillers to tailor the thermal expansion coefficient. Often the reduction in coefficient thermal expansion of the cured epoxy resin is proportional to the filler's degree of loading. Certain fillers such as zirconium silicate and carbon fiber have a negative coefficient of thermal expansion. These are very effective in lowering the expansion rate of the epoxy, especially at elevated temperatures. When two different substrate materials are used as adherents, the adhesive's coefficient of thermal expansion should be adjusted to a value between these two substrates. It is usually not possible to employ a sufficiently large filler loading to adjust the thermal expansion coefficient required to match the substrate, as high loadings increase viscosity to the point where the adhesive cannot be applied or cannot wet the substrate anymore. For some applications and some fillers, loading volume up to 200 pph may be employed, but optimum cohesive strength values are usually obtained with lesser amounts. Nearly all polymeric materials shrink during solidification. Sometimes shrinkage happens because of escaping solvent. Even 100% reactive systems such as epoxies and urethanes experience some shrinkage because their solid polymerized mass occupies less volume than the liquid reactants. The result of such shrinkage is reduced dimensional stabilities or the occurrence of internal stresses at the adhesive substrate surface. Reduction in this shrinkage can be accomplished by introducing fillers which reduce the rate of shrinkage by bulk displacement of the resins in the adhesives formulation. Unmodified polymeric resins are natural insulator and do not exhibit electrical conductivity. In certain applications, such as in the electrical and electronic industries, epoxy systems must have a degree of electrical and/or thermal conductivity. Electrical conductivity is of course important in adhesives that must make electrical incorporation between components and in adhesives that must provide electromagnetic or radio frequency interference, EMI and RFI functions. Thermal conductivity is also important in highly integrated electronic applications where the heat generated by the components must be transferred to a heat pipe or by some other means outside the electronic package. Increased electrical or thermal conductivity is generally accomplished by adding conductive fillers to the epoxy formulations. For optimum electrical or thermal conductivity, the particles must be so concentrated that they come into contact with one another, which requires such a high level of filler loading that other properties may be significantly degraded. Appropriate fillers have been used to produce epoxy systems with high electrical conductivity. Electrically conductive epoxy systems owe their conductivity to the incorporation of high loadings of metal powders or other special fillers. If enough metal particles are added to the network within the polymer, the matrix becomes electrically conductive. Currently, all high-performance conductive products are based on flake or powdered silver as it offers an advantage in conductivity stability that cannot be matched by copper or other lower-cost metal powders. Conductive carbon, amorphous carbon, or fine graphite can also be used if some degree of conductivity can be sacrificed for the lower costs. Conductive adhesives are generally formulated from base polymers that are low viscosity thermosetting resins such as epoxides. Where elastomeric properties are required, silver-filled flexible epoxy and silver-filled silicone rubber systems are commercially available. Moreover, sometimes higher thermal conductivity and better dimensional stability are required from epoxy systems. Most unmodified polymeric resins have a very low thermal conductivity. There are certain applications where high levels of thermal conductivity are required. For example, power electronic devices and other heat-generating components are bound to heat sinks and other metal sources. Metal powder-filled adhesive, such as those described earlier for electrically conductive adhesive, can conduct both heat and electricity. Some applications, however, must conduct heat but not electricity. In these applications, the adhesive must permit high transfer of heat plus a degree of electrical insulation. Fillers used for achieving thermal conductivity alone include aluminum oxide, beryllium oxide, boron nitrate, and silicate. Theoretically, boron nitrate is an optimum filler for thermally conductive adhesives. Beryllium oxide is high in cost and its thermal conductivity drops drastically when it is mixed with epoxy resins. Therefore, aluminum oxide, and copper fillers are commonly used in thermally conductive epoxy systems. Titanium or beryllium oxide also provide a degree of improvement in thermal conductivity to epoxy systems. Magnesium oxide and aluminum oxide have also been commonly used for this purpose, although the degree of improvement is not as great as the fillers discussed earlier. Thermal conductivity also helps to improve heat transfer during cure. This reduces exothermic temperatures and expands the pot life, particularly at high filler loadings. In this figure, the effect of various fillers on the thermal conductivity of epoxy systems can be seen. Non-conductive fillers are employed with electrical-grade epoxy adhesive formulations to provide assembled components with specific electrical properties. The effect of electrical grade fillers, for example silica, on the electrical properties of the adhesive is usually marginal. Generally, fillers are not used to improve electrical resistant characteristics such as dielectric strengths. The unfilled epoxy is usually optimum as an insulator. Also, under conditions of high humidity, fillers may tend to wick moisture and considerably degrade the electrical resistance properties of the adhesives. The one exception where certain fillers can provide electrical property improvement in an arc resistance. High hydrated aluminum oxide and hydrated calcium sulfate will improve arc resistance if cure is sufficiently low to prevent dehydration of the filler particles. Mineral fillers generally result in increased dielectric constant and dissipation or loss factor. Some mineral fillers, such as titanium oxide, have been reported to lower the dissipation factor of the epoxy systems. However, dielectric constant of epoxy adhesives can significantly be reduced by using fillers with low dielectric constant, generally polymers such as high-density polyethylene or PTFA. Hollow spheres containing air with a dielectric constant of 1 can be used as fillers to significantly reduce the dielectric constant of epoxy as well. By use of inorganic microballoons, dielectric constant as low as 1.5 have been reported at filler loading about 20% compared to a dielectric constant of 4.4 for the unfilled epoxy system. The majority of mineral fillers have a higher specific gravity than do epoxy resins and will therefore increase the specific gravity of the fully cured product. The increase in specific gravity is in proportion to the loading volume of the filler. Filler with a density lower than that of epoxy can be used to provide reduced specific gravity in cured products. These are usually gas-filled microballoons. The microballoons filled epoxies, sometimes called synthetic foam adhesives, are often used in marine applications where low density and buoyancy are important criteria. Other low-density microballoons based on phenolic and other materials have been developed for use in epoxy adhesive formulations as well. Only certain fillers can be used to increase the cohesive strength of the cured epoxy adhesive formulations. Generally, fibrous or flake fillers such as talc, glass fibers, or mica will bring about a certain degree of increase in the tensile and flexural strengths. However, for significant increase in physical strength, a relatively high concentration of the fillers has to be used. Particulate fillers usually reduce tensile and flexural strengths. Impact strength is generally adversely affected by the particulate fillers. The addition of particulate fillers generally decreases compression fatigue but increases ultimate compressive modulus and compressive yield strength because of a stiffness effect. The reinforcement of epoxy adhesive has typically been achieved through the use of fibrous and flake fillers. Surface-treated wollastonite or calcium metasilicate, which is a fibrous mineral filler, is also employed to improve adhesion to the epoxy matrix. It can be applied at relatively high loading levels, which yields high strength and improvement in moisture resistance. Talc or hydrated magnesium silicate is another mineral that is used to reinforce epoxy adhesives. It has a plate-like structure that provides good stiffness and creep resistance at elevated temperatures. Calcium carbonate filler is a particulate filler which can improve the physical properties of epoxy resins such as tensile strength, tear, and elongation. The combination of particle size and surface treatment is critical in the selection of precipitated calcium carbonate fillers to obtain desired properties. Fillers improve the thermal properties of the cured epoxy formulation by bulk displacement of organic component. This reduces long-term shrinkage and thermally induced weight loss. However, the glass transition temperature is not significantly affected and in some cases may be lowered. The main effect of fillers on thermal properties is achieved through improvement in thermal shock resistance, which is achieved via modification of the thermal expansion coefficient. Mica and fibrous fillers used in relatively high loading provide very good improvement. However, their use is often precluded due to their handling difficulties. Fillers having high thermal conductivity will also increase the heat transfer in the cured epoxy system. The improved heat dissipation will result in improved thermal cycling properties. Aluminium powder in particular is frequently employed at a relatively high concentration in high temperature epoxy adhesive formulation. The filler provides improvement in heat resistance and increase the thermal conductivity. Filler often have a significant effect on the moisture resistance, the moisture vapor transmission rate, and the solvent and chemical resistance of the cured adhesive bond. The effect, however, can be in either direction. Some fillers, such as calcium carbonate, tend to lower acid resistance, whereas others, such as silica or aluminium, may tend to lower alkali resistance. Many fibrous fillers exhibit a wicking action for moisture. And this is particularly true for high surface energy glass fibers, and especially when the fibers are exposed, such as when the cured epoxy is machined or a crack formed in the adhesive resin matrix. For this reason, glass fibers that are used in adhesives are often treated with a coupling agent such as an organosealant to improve the bond between the fiber and the epoxy matrix. Fillers have a very little effect on the actual adhesion mechanism, since most of this is controlled by intimate contact of the liquid epoxy and the substrate. However, fillers improve the measured adhesive strength of cured epoxy joints by decreasing internal stresses related to shrinkage and differences in the coefficient of thermal expansion. That's why a significant improvement in tensile shear strain with the addition of fillers can be often seen. Fillers also provide for a method of controlling viscosity so that a predominant and regulated bond link thickness is possible, which improves adhesion. The degree of tensile strength improvement often in the range of 50 to 100%. Although the addition of fillers also result in an improvement in the tensile shear strain, it also often results in a decrease in peel or impact strain. This is due to the reduction in elongation and toughness that is often accompanied by the high filler loadings in epoxy adhesive systems. Fillers generally lower the curing reaction rate and reduce the degree of exotherm. This is primarily due to their build diluting effect and the resulting increase in thermal conductivity. The more filler added, the less will be the heat evolved during cure. However, even with highly filled epoxy system, the filled resin is still a relatively poor conductor of heat. Thanks for your attention. I hope you enjoy. Please share your thoughts, comments, or questions, and I will come back to you soon. Thank you.